Oh, you can do whatever you want. Just want this to be fun and interactive.
All right, let's go ahead and get started. Today will be our first tutorial, and I'm going to introduce Sarah. Sarah is a senior lecturer, which is assistant professor at the Cobb Faculty of Computer Science at Technion Israel Institute of Technology, where she leads the collaborative AI and robotics Clara Lab. Before joining Technion, Sarah was a postdoc fellow at Harvard University School of Engineering and Applied Sciences and Hebrew University of Jerusalem. She received her PhD from Technion. Sarah's research focuses on providing theoretical foundations for designing AI systems that are capable of effective collaboration with each other and with people. She has received several awards, including the ICAPS 2020 Best Dissertation Single Mention, the ICAPS 2014 Honorable Mention for Best Paper, the Eric and Wendy Schmidt Postdoc Award for Women in Mathematical and Computing Sciences, and the Weizmann Institute of Science National Postdoc Award for Advancing Women in Science. And Sarah's work has been published in leading conferences and journals for AIs and robotics. So yeah, take it away, Sarah.
Thank you. So good morning. Just to kind of, so I understand the crowd, who here has experience with robotics to some degree? Great. And what about planning, like task planning, motion planning, control? What would you classify yourself as doing? Task planning, high level, or more control, low level? Anybody from motion planning kind of background? Okay, great. So I hope this will be an engaging tutorial for you guys, giving you maybe a broader perspective, trying to kind of integrate the different themes. The barcode is a link to the Git repo where all the materials, including this presentation and the notebooks that we're going to run, they're all notebooks that you can run. I'll explain in a bit what is required to get them to run properly. So as was mentioned, I'm the lead PI. I'm the PI of the Collaborative AI and Robotics Lab at the Technion. I joined the Technion 5 years ago, and all through my master's and PhD, I was doing automated planning. So mainly in the symbolic space, and it was during my postdoc at Harvard where I started thinking about extending kind of my horizons to new domains. And so I started working on the one hand on reinforcement learning and trying to figure out how to incorporate model-based reasoning into reinforcement learning. And I also started working on robots because I thought that the idea of working at different levels of abstraction is fascinating. So now my work at the lab, the work that we do at my lab can be characterized by either providing theoretical foundations for multi-agent AI, so more on the algorithmic side, but we also work on robotics, multi-robot systems, and actually multi-agent energy systems is something that I'm very passionate about. So so the work that we do, and I think you'll see this in the way I'm going to present the topics that we're going to discuss, focuses on the integration of model-based reasoning and knowledge. And I think the conferences, the two conferences that we are attending are actually about that, right? Fusing the physical world, the continuous space, and the abstract space, which is something that I think is fascinating. And what I'm going to talk to you about and try to motivate is this need in today's very rapidly evolving world and rapidly evolving AI, this need to think about ways to bridge AI and robotics. So in this context, I think that I find that the frontier of harnessing and incorporating abstract reasoning into the physical space, into physical world, is something that is still very challenging and there is a lot of work to be done there. And this tension between abstraction and the physical world is something that we can do. There is a lot to do there, a lot of challenges, and specifically in robotics, where the physical world, the continuous space, needs to be represented in a reliable or in a loyal way, in an effective way, in order to actually get the robots to perform well. I do not adopt the end-to-end approach. I hope this diagram depicts this well. So the models or the analysis that we're going to do today captures the different components that go into decision-making in robotic agents. So not end-to-end decision-making. That's a very, very popular trend. There is a lot of very good researchers that are working on that, but that's not the kind of work that I do. I like to decouple the different components. And specifically, I like to work on multi-robot systems or multi-agent systems, where you need to also think about the interactions between agents. So we're not going to discuss this today, but so we're going to just focus on one agent and the decision-making procedure of an agent. And my claim, my view is that if we are interested in promoting a physical AI, so AI-enabled physical systems, these agents need to have a lot of capabilities that are connected to the topics that we're going to talk about today. So we are interested in agents that can understand the environment, that are not necessarily given the state of the world, but actually need to extract it from their sensors. They need to reason, they need to plan, they need to act in the environment, they need to take an understanding of what their actions actually cause, and they need to adapt to uncertainty and failure. So all these provide extremely challenging problems to solve. And of course, these systems, I'm not going to talk about foundation models, and I know this is, or I'm going to talk about it towards the end, the effect that foundation models had on robotics. But I do want to emphasize that this is not going to be about I'm not going to show you how to use foundation model for robotics. I'm going to discuss what are the components that are needed for reasoning in a robotic system. And each of these components can be implemented using whatever foundation model that is out there and that happens to solve the problem. So again, I think this is a frontier that is that is still not totally completely captured or totally solved using these very powerful tools, but definitely are relevant. They're very relevant for integrating them into our systems. So I wanted to start just by giving you an example of the kind of interaction or the fusion between high-level reasoning and low-level control, or high-level reasoning and actuation that happens in my lab. This is work by a former student of mine, Yuval, who used here POMDP, partially observable Markov decision process, to understand how best to intervene in order to assist a robot. So the robot on the right has some very long horizon manipulation task, where it needs to place the cups on the table and pour soda into them. However, the can is unreachable, and another agent can assist by moving one of the obstacles. And the assistive agent, the helper, needs to reason about the knowledge state of the actor, about the way it can provide assistance, about the effect of this assistance, whether to move a block that is maybe blocking a configuration pose, or maybe to move an obstacle that is obscuring the view, to causing one of the cans to be occluded, or one of the cups to be occluded. So all this reasoning process is extremely complex. It has to take into account information that is arriving from sensors. Nobody gives you the states. You actually have to extract it from the sensors that are on the robot itself. So that is just an example. So a PONDP robotic agent. And of course, we have other examples of projects. I'm going to discuss some of them during the talk. But the idea is that this integration between these high-level AI ideas and the robotic settings that we care about, since we want the robots to do complex tasks and complex reasoning, we have many ways to create these interactions. Yesterday, I presented, just to give another last example, yesterday I presented this work. This is a work where my student Guy used a VLM to produce a probabilistic belief, a state estimation for the robot, and use that to perform robust planning. So we extracted from the VLM a probabilistic estimation of each of the features of the environment and produced a belief set on which he could then perform planning. So robust planning basically means that you want a plan that succeeds for all the states that are in the belief set. And okay, so I don't know, this is, it's a kind of a very, there is a lot of variance to the way this tutorial goes. This is a tutorial that was originally created for ICAP's summer school. So we had 2 hours a day through 5 days. So I could evolve the materials very, very slowly, but now we have 3 hours. So I try to adapt the content to the time that we have. But I do want to emphasize that all the materials are online and available, and you can be in touch if this is of interest to you. There are, in principle, 4 labs on the website. So all of them are Google Colab notebooks. If you are actually interested in running the notebooks, this is the link. I highly recommend it because it's going to be boring for you otherwise. So each of these notebooks has this button that you can press. You can, of course, run everything locally, but it's going to be harder you're going to have to install whatever is missing. Yeah. And what you will see in the notebooks is that you have some questions that we pose for kind of engaging some debate or some, we wanted to create some ideas, to kind of generate ideas about some issues. Then you have tasks with areas where the code is missing. There are very small snippets of code that you can complete, and you have these stop signs that come before the answer. So if we have a question, after that we have the solution, or we have a task. So I hope you are familiar with notebooks, so you can just run the next cell and you would have the solution if you're not interested in solving the challenge. For the second and third notebook, you will have to use the GPU, but the one that is provided for free, nothing too fancy. It's just because we're going to do motion planning with a robotic simulator, Mujuko, and that requires a bit more compute. Questions so far? I don't like talking for too long straight, so I'm very interactive. I barely finish 3 sentences when I teach without asking a question, so be warned. Okay, so now let's dive into the content. I'd like to motivate integrating task and motion planning. So from what I understand, some of you are working on continuous space, motion control, motion planning, motion control. and maybe some others are working on task planning, but I want to motivate the integration. So the most canonical problem that has been the canonical example for task planning is blocks world. You have, you know this? Anybody knows this? So you have an initial state of blocks, and you have a goal state, which are the configuration of the blocks. And the challenge is to find a plan, hopefully an optimal plan, preferably an optimal plan that gets you from an initial state to a goal state. And the way we represent this in classical planning is with a language called PDDL. Anybody familiar with that? Okay, so in PDDL, you have your types, here only blocks, and you have your predicates, so your Boolean features expressing in a lifted way what are the features of this environment. So in this environment, you are interested in understanding whether block B1 is on block B2, whether a block is clear, etc. Then you have actions, and actions are again parameterized, of course, because we do not want to specify the grounded space for a reasonably sized problem. So we have parameters, and here, in order to stack a block on another block, you need to be holding the first block, and you need the second block to be clear. So these are the preconditions, and the effects are that you have delete effects and add effects. So this is the standard way in PDDL to express the effects. So here, when you stack, you're no longer holding the block, or the robot is no longer holding the block. The second block is no longer clear, and now B1 is clear, the hand is empty, and the block B1 is on B2. So what we have here is the domain description, and what we have on the right is a specific initial configuration. So in this case, we have 4 blocks, and this is the initial configuration and the goal configuration, which is the fact that this is the configuration of the tower. So this is great. We have this very general language with which we can express any problem that can be expressed using these features. And I think this is an effective language even also for probabilistic domains, the fact that we have symbols to kind of define in a general way what are the interactions. And it's also a very complex problem, so we can spend all our research career just investigating more and more elaborate search approaches, because even though the solution approaches are polynomial in the space, in the size of the state space, the size of the state space is exponential in the number of features. So we have a lot of fun in inventing new algorithms. But when we want to take this and actually implement it on a robot, we have many challenges, right? We have this plan, pick up B, stack B on D, pick up C, stack C on A. I spent 10 years of my research at that layer of abstraction, right? This is what I was doing, picking up, just figuring out plans where pick up B was an atomic action that I considered to be executable. But now when we want a robot to actually do it, many problems arise. What is a block? How do we know that a block is present? Where is it on the table? If it's on the table, where is it on the table? If you want to actually pick it up, it's not enough to just mention this very general statement about being on top of the table. How does the robot know how to stack? And how does it figure out what the best way to pick up objects is? super complicated. And here is where the fusion happens between very different research communities. So let's understand what a robot is. And of course, this has many interpretations, many kinds of robots. But the idea is that we're going to discuss a general framework that is suitable for all these robots. You can have aerial robots, you can have manipulators, you can have mobile robots. I'm not going to talk about the swarm robots, because those are not performing complex reasoning, so that's not part of my research, but those are arguably also another form of robot. I'm actually in the process of trying to buy for my lab a robot that is mobile and a manipulator on top of it. So this guy here is actually barely used. So I want to actually get it to go on a vehicle. So that's going to create a lot of interesting problems. But in general, when we talk about the robots, we have three elements that we need to distinguish between. So we have the sensors, understanding how the robots perceive the environment is key, because the sensors are our way of interacting with the environment. We have controllers, decision-making procedures, and we have various actuators, various ways of changing the state of the world. And at the same time, we have three processes that we need to take into account. So state estimation is about maintaining a representation of the current state of the environment. Decision-making is about mapping that belief, this is understanding of the state of the world into actions. And motion control is actually translating these decisions into motions, into actions in the environment. And these different components go into the three, into this decision-making loop that the agent, this is the canonical diagram. You have an agent, it takes actions, it perceives the environment through its sensors, and then needs to decide how to act. And all this is happening in continuous space, and the way we abstract it is going to be the challenge. How do we take this problem this action that we need to perform? How does this translate into these three components? So we said, right, so this is the problem, this is the definition of the problem, the action we want to apply. And we said we had three components. We had actuation, we had sensing, and we had decision-making. Where is each component? Where is sensing? Where does sensing come into play?
In determining the precondition?
Yeah, so great. In determining the preconditions, what about actuation?
The action itself.
The what?
The action.
Yeah, but so the action itself, right? It's not in the definition. So the definition of the problem is actually on the state space, not on the actuation, right? So it is a result of, so this is actually defining what the state we want to be in is, and that is actually induces the way we perform the control. And of course, the state estimation is in the preconditions, the decision-making is in the decision of which action to perform. And then we need to make sure that our control, our continuous control actually establishes the features that we want to achieve. Okay, so I just wanted to do all this to convince you, and some of you are already convinced, that task planning is not sufficient. So thinking in an abstract level would not be sufficient to actually deploy a robot in an actual physical environment, especially if this is not a fixed environment. And of course, things get get very messy very quickly when we have varying costs, when we want to avoid collisions, when we have other agents in the environment, et cetera, et cetera. So autonomy of a robotic agent is something that we need to define if we want our robots to do interesting things and do them safely. And the paradigm that I adopt in my work, and I think has become very popular these days is this agent-based view. So what we have is an agent with actions, with a set of actions that it needs to decide at its point which action to perform, and it doesn't matter if it's what kind of entity this decision-making procedure represents, as a robot, a person, a video game, whatever. The action is performed, and then we receive observations and rewards, and maintains the belief. So this is already a very complicated problem, but when we have multiple agents, not our focus of today, things become even more complicated. So the first slide that is actually about task and motion planning is this one. And it is a very important one because it kind of clarifies, I think, one of the key complexities of getting agents to operate in the physical space. The physical space is continuous. There is the environment, there is the robot dynamics, the dynamic of the agents, and there are sensors that actually exist in the physical environment. These components interact with 3 layers, and each of these layers has traditionally been investigated by a separate research community. So you'd go to a controls conference, you would meet people that think about optimal control in a very high frequency decision-making procedures, with state estimation that is relatively low level, understanding the sensors, understanding the state of the robot itself, without having the ability to, because of the complexity of these the problem, having the ability to think ahead. Then we have the high level, the mid-level layer, which is the motion planner. The motion planner moves in the physical space, or computes a policy for moving in the physical space, again, trying to understand the scene, but capturing the components that are relevant for the motion planner. And that happens at a higher frequency, lower frequency. And at the high level, there is task planning, which is the thing that I've been doing for most of my career. And then that happens in an abstract layer. How do we combine these components? That's the key of today's tutorial. So we're going to use this example that I created, and we're going to use this later on. This manipulator robot that has objects on the table, and let's say a person says that it wants food. How can we get this robot to perform this very complicated task while accounting for the different components that are there, understanding first how to accomplish the task, and then what the high-level strategy for accomplishing the task, and then how to actually move in the environment. So what could be considerations for this robot that needs to bring the person something to eat? What kind of consideration might arise? Let's say that the robot knows exactly where it is, because this is a static robot and it's moving. It's with these kinds of robots, it's very easy to monitor where the end effector is. So localization for the robot is not an issue. What can come up when you want to,
does it know which object is food?
Does it? Well, that's a question, right? What is food? Which of these objects is food, right? What else?
Is an object food by another object?
Exactly. What are the objects that the robot can actually grasp, right? What is occluded by other objects? Other considerations?
Reach the object.
Can it reach, right? There is a limitation to how far it can go. Also, once it reaches an object, this is a robot, it's a machine, it's made of metal. What happens if it tries to grasp a banana versus an apple? Well, both are quite soft, right? But maybe one of them is even softer. If it tries to reach the banana, it might drop the lamp. These are high-level considerations, right? Understanding that this is a lamp and a lamp might break if you try to grasp it is something that cannot happen at the physical continuous space. That's an abstract notion that we need to have a robot take into account when choosing which piece of fruit here in this case to grasp. And these are, there is a strong motivation to propagate information between the layers. So, right, if something is unreachable, that's something that the task planner does not have that information. If we have this high-level representation, we need to capture the capabilities of the robot, but then again, also understand how these capabilities can be translated into effective actions. So we start by understanding that the physical world, this interpretation of the physical world is the first challenge, right? Understanding that this is an apple, understanding that this is an apple, this image here is quite easy these days. This is an analysis performed by YOLO. I'm assuming that every day that passes, we have a new tool, right? So this is from 3 months ago, probably outdated. So we have better and better tools to understand that that is an apple. What about this? If this is what the robot sensors indicate, that now becomes that now we are actually under higher uncertainty, right? If this is the only information that the robot has about the environment, right? So now the challenge is even harder. Then the high-level decision-making is captured at the abstract level, right? So is the lamp on the table? Is the lamp fragile? Is apple food? This is actually something that foundation models are extremely effective these days at providing us with relatively reliable estimations when the image is clear, when things are quite straightforward, when there are no occlusions, no need to kind of reason about the long term. And there are a lot of off-the-shelf effective tools for performing this. And still, we need to know what information to extract. I can tell you that the first time we used, this is an image from the internet, but I actually have these robots. The first time that this robot was deployed in my lab by, so the first test that we performed, we tried to grab a cup. I always carry a reusable metal cup, and we used it in the experiment. So the first time we used our robot, it actually tried to grasp the cup, and it got cut. The robot had this rubber protection band, and it was completely destroyed because we didn't take that into account, right? The metal cup, because the robot has such a big force, it did not stop, and we ruined the robot on the first attempt. This is not something that the task planner that we ran had any information about, like how dangerous the cup is to the robot. These kinds of things are the things that happen when you try to actually actuate your policies. So just to have a definition of what task planning is, task planning in its simplest form, or maybe not the simplest form, but a very standard form, is that we have a discrete environment, we have state space represented in the symbolic space, and we have actions. As I said, in the models that I use and that are in the tutorials, we have actions that are modeled via preconditions and effects. So, and in task planning, we have an initial state in the symbolic space and a goal condition, again, in the symbolic space, and we are trying to find a sequence of actions that achieve the goal state in its maybe most general form. This is a partially observable Markov decision process, where in addition to the state space, action space, transition function, and reward function, we also have the observation space, omega, and the observation the sensor function and some initial belief. So as I said, once you start working with embodied agents, figuring out what is the right representation for your state space and how to deal with the probabilistic sensor model is a challenge, right? Anybody work with MDPs, POMDPs? Anybody? Yeah. So we're used to getting these, defined, right? Yeah, P takes us from S to A to some distribution over, that doesn't work with sensors. They're super noisy. Nobody gives you out of the box transition function, and it becomes really challenging. So we can work with generative models, we can work with simulators, and yet it's hard to kind of figure out what is going to be an observation that that the robot is going to see when it takes a future action. So simulating these things becomes hard when you actually want this to be deployed on an actual robot. The next layer, motion planning. So let's say the robot decided that this is the apple it wants to pick up because it figured out, taking all the information that we encoded at the task planning layer, the fragility of the lamp, the distance that it can cover, et cetera, et cetera. Now the robot has a decision. The objective is to pick up that apple. What happens then for motion planning perspective once we have a decision of which object to pick up? Motion planners, yeah.
Needs to plan a path so it can grab it without hitting any other objects.
Without hitting any other objects, right? So all the other objects that before in the task planning layer were bananas or boxes or apples, now they become obstacles. In this space, we're worried about not colliding. Of course, there are motion planning paradigms that are evolving and gaining popularity, where you actually are allowed to collide with objects and you can perform actions that actually use the environment to move. But for simplicity, let's just assume that we're in the traditional paradigm where everything is an obstacle, including the robot itself. And the goal is, how do you express your goal? What is the goal here? It's not apple. You can't say anything about the apple. How do you define your task? We're in the robot's space, which we call configuration space. So what is the planning problem here? Well, it's about configurations. It's about, well, in this case, what we model is the end effector and the position of the end effector. Why? Because we want to pick up the apple. And we have this pre-knowledge, so we have this domain knowledge that allows us to kind of assume that once we get the end effector to a certain position, the object will be possible to grasp the object. So that's motion planning. It happens in configuration space. We'll talk more about that. So you have a robot system with d degrees of freedom, which means that those are the controllable elements. And let's assume for simplicity that the environment is known. What you want to do is to take your robot, defined via its degree and the elements and that you can control, defined by the degrees of freedom. So the dimension of the configuration is D. You want to take your robot from Q0, so that's the initial configuration, to Q goal, which is the end configuration. And you want to find a collision-free continuous path. So that's motion planning, and completely ignoring everything that happened at the abstract space. And a lot of my colleagues, roboticists, this is the space they live in, but there is another space, which is the space of control. And I think probably some of you are work on kind of understanding how control works. Here, the horizon is typically short. And what you want to do is, once you get a plan from the motion planner, you want to execute it. The motion plan is defined by a sequence of configurations. So the control will take you from one configuration to the next. Again, typically, this is done without considering the motion planning layer, assuming that there are no obstacles because that this command was prescribed by the motion planner. There is no need to take into account any obstacles, and then you compute your trajectory. So I'm not going to focus on control today because there is just so much to talk about, but so it's mostly about task and motion planning, but I think it's important to also understand that motion control is there and sometimes taken as input for the motion planning algorithms, but still a very important component that actually performs, then monitors the execution of the robot. So we have these three layers of abstraction, and we need to think about how to get them to interact in order to perform complex tasks. If you want to just train your robot on picking up known objects from a table, maybe you can avoid a given understanding. You can just do end-to-end learning. But if you actually want to perform complex tasks and do them efficiently and take uncertainty into account, I think it's important to decouple these components more so if you want to work with multiple agents. That becomes a mess. And when I say mess, I mean good mess, like research kind of mess that we actually enjoy. So the infrastructure that you're gonna play around with today is our interpretation of integrated task and motion planning, where we have a state estimation component, decision-making component, and a motion controller. We implemented these in a very specific way, but of course there are various ways to implement these. Our environment, of course, is going to be a virtual environment, a Mujuko, and we are going to use PDDL for representing the task planning space. You'll see how that goes. So let's start with task planning. Let's consider the kinds of things that we can do with a task planner, assuming that we have this nice representation of the environment and of the task and of what it is that the robot can do. And this is a more elaborate definition. Here today, we're gonna assume that we have a deterministic model of the task space. It's gonna be interesting enough. And of course, for task planning, we have various solution approaches. I cannot cover all of them, but the focus of the notebook is going to be on a best first search. So specifically, you're gonna run variations of A*, where you have this iterative expansion, so forward propagation from the initial state to a goal state. And I hope that you will engage with me in actually trying out the tutorial. So the first lab, do you guys, okay. So I'm gonna assume that you are interested in this because I think that the people that are actually going to do this are going to enjoy this. So what I'd like to do now is lab number 1, where I'd like us to practice at solving the blocks world example. So specifically, this is meant to actually emphasize and give us an idea of the challenges of integrating task and motion planning. So when we pop a node from the frontier, when we do A*, we iteratively, we maintain a frontier. When we pop from the frontier via heuristic. So the challenge is there in task number 1, where you are going to compute a heuristic based on the domain description. As I said, the idea is for you to play around with the code. So if you are, if you are not interested in actually solving the task, you have a solution right below the definition of the task. But this is going to give you an idea of how would we define task planning and what are the limitations. So I think we'll take until 10. So to give you guys an opportunity to solve this, and I'm gonna bring, just in case you are interested, I'll put the barcode again so you can see where you can download. Well, you don't need to download, it's all online. Here is the barcode if anybody needs it. And if this doesn't work, just there is a GitHub of my lab. And as I said, the tutorials are meant for a longer time. So I think it's best if you focus on task number 1. And then, yeah, so this would be running A* with a heuristic. Of course, I'm here for questions if you're interested. Of course, it would be super cool if you can get a result that's better than ours. I think our best result is 30 expanded states. Oh, no, iteration. Yeah, expanded iteration count, expanded states, but. Yeah, super interactive. It's not.
It's not the big room.
Yeah.
multi-line strings.
So just in case you're interested in joining, I'm gonna put the barcode again so you can see. We're doing the first lab in this repo.
Can you give us an example of the heuristics here?
Oh, it's actually you can see in the solution, but one very popular example is the delete relaxation. So you ignore delete effects.
Ignore what?
Ignore the delete effects when we define a problem where we have, so when we define the effects of actions, we have delete effects, so what becomes false, and this is what becomes true with all these dead effects. So if you ignore the delete effects, the problem becomes much easier, but of course unfeasible because you ignore the delete effects. Now the block can be both. So block B2 can be both clear and have block B1 on it if you ignore those, but computation becomes super effective. So that's an example of the relapse problem. But you can just also count the number of predicates that are missing from that you haven't achieved in the goal statement. That's a much easier one to implement. You just count the number of predicates that are here, and you try to figure out how many are missing. The problem that's we're going to the details, but what I'm describing for is admissible, meaning that it's an underestimation of the true cost. And if you count the number of missing predicates, that might be inadmissible, because they have one action that can achieve more than one predicate. Thank you so much. So let's take another 3 minutes. Is that okay for you guys? And then we can move on. And of course you can continue. This was just to get the hang of like what planning people are do with their time I once spent 3 months formulating a heuristic and proving that it maintains the optimality. So can become quite complicated. No, I just forgot. I didn't realize I was occupying the slots. No, I'm fine. I have a convert.
Also, if mic is too loud for me, there's a control for that.
You actually have to say. I sometimes I tend to speak too loud, but I'm doing okay right now, right?
Yeah, it's great. I'm just wondering if you're not okay with it, you can.
Thank you. So how did you do? Did you guys manage to compute a heuristic? Anybody manage to beat our 30 node count? Or maybe you're still thinking about ideas. In any case, I hope this gave you, is that okay? Can we continue? Yeah, okay. So I hope this gave you a flavor of the kind of challenges that are involved in task planning. Of course, again, these notebooks are available. The idea was to just give us an idea of how we can approach these settings. The idea here in the PDDL language is that we can compute general domain agnostic heuristics and achieve good results. But of course, when we want to solve a robotic task, a lot of the things cannot be captured, or at least were not captured in the PDDL representation that you saw. So what was not captured, for example, in the pickup block kind of setting? We've already discussed some of these aspects, but what is not captured?
What if there's ambiguity?
Sorry, what?
What if there's ambiguity in the task? Definitely.
Yeah, so what kind of ambiguity can occur?
Like in the case of the food one, do you pick up apple or the banana? In case of picking up food, do you pick up apple or banana?
All right, but here in this task, in the blocks world task.
If you say pick up a block, which color block?
Which color, right? Or I say yellow, or I say 1. What does it mean, 1, right? This is a physical environment. What is block 1? How do I know which one is block 1? And if something happened and moved, how do I monitor the fact that, this is block 1 and not this one? What is on table? Block on table, what does that mean? How do you translate that into an actual execution of a robot that actually needs to pick it up? Table is not specific enough. And of course, the fact that we assume that these actions are atomic actions of one computation. We didn't take time into account at all, continuous time. So a lot of the things, a lot of complexities were not captured in this simple example that we saw. We did not account, even in the realm of task planning, we can extend models to account for various sources of uncertainty, reward functions, discount, all these things that we're used to doing in planning. But we have to account for very specific complexities that arise when you actually want to deploy this robot in the physical space. How do we know that block B is on table 3? First of all, the fact that it's block B, that it has a name, is something that we need to maintain. But here, nobody tells us that this is the block. Even if we're looking for a red block, we need to remember that what we get is an RGB image or a depth image. The robot needs to extract this information while acting in the environment. So we have this continuous stream of sensory information that we need to interpret, and we need to update our belief as we gain more information. So for example, here, we sample this image and we see this red area, and we can, assuming that there is only one block and that the block is red, we can condense the belief. Our uncertainty now here is reduced. Anybody knows this representation, what this means? What do we do? I mean, I'm not going to go into the details of how this is actually maintained, but anybody familiar with particle filtering? Okay, so this is how we do this here, right? We have a hypothesis, a set of hypotheses that we maintain, and then when we gain information, we can reduce uncertainty. And I'd like to give you an example of a complexity that arose in one of our projects, where we had this robot, this actor robot, is manipulating an object, and the object falls. So there is uncertainty in execution, but this robot does not have an active sensor, and the helper agent needs to help the actor by providing an observation. But because this is a time constraint setting, and also maybe a setting where the helper itself has a task, it needs to decide where to observe. And what we show here on these 3 images is that, this is the object. Let's say this is the configuration that the object is in now, but this is the observation. What is this? Anybody familiar with this interpretation of the observation?
In configuration space.
No, this, yeah, but the definition in configuration space, what kind of analysis is this? When we try to, the analysis that they performed here is in intersection of unions. So we analyzed the space to kind of capture the dimensions of the object. And to give you an idea of why this is a very, this is the contour of, so what we did here was we tried to simulate what is going to be the observation when the robot, the helper robot, observes an object that is in specific configurations, right? And why we're talking about this just because I want to give you an example of how we integrated physical space into high-level decision-making. The robot, the helper, needs to decide whether this is an effective sensor configuration. So we needed to predict what is going to be the observation, what are possible configurations of the object after it falls, and understanding whether this is going to be effective observation, in the sense that after this observation is provided, the actor will attempt to grasp the object, to re-grasp. So the information that is provided here is going to affect the belief of the actor and hopefully help him. Is this an effective sensor configuration? Assuming that these are the 6 possible configurations of the object, and all these are observations that are taken from the same sensor configuration for these specific 6 objects. Is this a helpful sensing configuration? This one, depicting here the 6 possibilities. Helpful or not for the grasping task? The helper, the actor, after receiving this observation, is going to go to a specific location and close its grasp. to try and attempt to pick up the object. Is this helpful or not in that sense?
Seems very challenging to know how we orient or manage to grasp it.
But that's true, but assuming that it receives this observation, does it know how to grasp the object?
Nowhere to go.
And it will try, right? It can use from this what is the grasp configuration, right? Where to go in order to close its grasp. But I don't know ahead of time if, so it's going to receive one of these six. So I'm asking whether it's going to be helpful for the sensing agent to send the observation from this sensor configuration, and these are the six possibilities of what it's going to receive. Is this helpful or not for the grasping test? Under the assumption that what the actor is going to do after receiving the observation is to go to one location and close its grasp. Helpful or not?
Is it sending which configuration as well as
No,
the?
just an observation. Great question. Just an observation.
Well, then no, because then it won't be able to,
It's not helpful.
because there's no context, so it doesn't know. This isn't enough information to figure out where it is, because there's all these different possible configurations.
The configuration is, so the robot brought the object, so there is a specific configuration that it's at, but I need to decide ahead of time where to sense the object from. So this corresponds to one sensing configuration. I just don't know ahead of time what I'm going to observe because I haven't from there. This is a prediction of what actually the helper is going to observe. So the answer is that in this case, it is a helpful configuration because all these four object poses have the same grasp. So if the robot receives any one of these, it will know where to go. It won't be able to distinguish between these four, and that's okay because it's going to they all correspond to the same grasp. Certainty here is high with regards to task success. Because sensing has to be task aware, and we need to integrate that into the decision making process. So task planning versus the real world, we have many aspects that are not captured. Specifically, the fact that we assume the state of the world is known or can be predicted or can be, we have some probability distribution over the states that's often non-realistic. We have unexpected outcomes that are not modeled or are hard to model. And of course, we have this tension between the discrete and continuous spaces. So now, let's talk about motion planning. So we talked about task planning and its limitations and the fact that there is a lot of work that needs to be done in order to perform task planning on actual robots. Now that we've decided that we want to attempt to pick up the block, now we need to understand in motion planning how to reach that position. Assuming here that we know that for a given object, we have a configuration from which it can be grasped. In the robot simulator that we'll have in the tutorial 2, we're going to have a suction gripper. So this needs to be just actually in small distance from the block, but we can of course have different kinds of manipulators. So the question that we ask here is how to get from one position to another. And even after we kind of figure that out, we need to understand how much force to apply, how to move fast and in an accurate way between positions. And of course, how do we verify that the result that we intended to achieve was actually achieved? For example, that the block was not dropped. So let's understand how the world is represented in the motion planning space. This might be familiar to many of you, but here we talk about degrees of freedom. So the elements that we can control. What is the degree of freedom here? Or what is the dimension? How many degrees of freedom do we have in this simplified door example? Only one, right? The angle of the door. Here, we have two, right? X and Y. And here, we can rotate the volume, so we have 3 degrees of freedom. The robots that we're gonna use have 6 degrees of freedom, so they have 6 joints that we can manipulate, and if we have a gripper, we have extra degrees of freedom, but we ignore those. We just assume that what we are focusing on is getting the end effector to the desired position, and from there we can just close and open the gripper. And in this context, people typically talk about workspace and configuration space, but I'd like to talk about 3 spaces because I think it is important to capture the 3 dimensions or the 3 abstractions. So the task space describes the variables that are relevant to the task. The abstract space, I want food. I want, the lamp is fragile. The workspace refers to the physical environment in which the robots operate. And that includes the positions of the objects and the obstacle that exists. So, and the map that you might have, or the representation of the dimensions of the objects. And configuration space is in the dimensions of the degrees of freedom of the robot. So what I like you guys to do now, and I didn't do, I now realize that I didn't do a QR for this, is to use this link to understand. This is a link that helps us understand the tension between the workspace, where we model the object and the robot, etc., and the C space, the configuration space. So this is a link. This is too hard, I can skip this part, but it's actually quite fun to understand this tension and why this is such a hard issue. It is a what we basically see here is a robot, a very simple robot that has 2 degrees of freedom, or actually, we can move the location, so 3. But we're considering here this representation in 2-dimensional space. So this is the workspace. This is the robot itself in its dimensions. And this is its configuration, its representation in configuration space. And what we can do here is we can add obstacles. And this is the representation of the obstacle in the C space, in the 2-dimensional C space. So what this means is that, what does this mean? This took me a really, really long time to kind of figure out. Where is the robot? In the C space.
The plus position.
Yeah, that's the plus. So basically what this means is that if you want to get your robot from here to here, is it possible? It actually is here in this space. If we're, well, it depends what we assume about the space, right? But if we add another obstacle, for example, here, I think this will do the trick. Oh, no. We have to block it. We have to make sure that there is no path. Right now, there is no path to get us from here to here. Okay, so this is how we plan in C space, in configuration space. And these are spaces that are not trivial to construct. But now, if we do have this representation in C space, we can plan with these representations. Okay, so that was a depiction of the representation. And the thing to understand in this context is that if we are given the dimensions of the angles, so we have the degrees of freedom of the robot specified for here, the angles of all the joints, understanding where the robot is and where the end effector is quite trivial. We call this forward kinematics. Tell me what the angles are and I can compute quite easily where the end effector is. What is the challenge? Where is the challenge? Why is this? What is going to be challenging for us? Given the end effector desired position, computing the angles that achieve it is going to be a hard optimization. So the first direction is super easy, we can quite easily, but doing what is called inverse kinematics is a very challenging problem, and that's what you're gonna attempt next. So again, remember that what we're interested in the workspace is the end effector position. How many possibilities we have for achieving a single configuration?
Just one with 6 degrees.
Yeah, we have 6 degrees of freedom. How many options do we have to achieve that specific configuration? Typically,
Just one.
oh, no, we have infinite ways because the joint space is infinite. So that's continuous space. Thank you for that. So we have many options. And, you know, this is, if I want to grasp the cup, this is a different configuration than this one. Okay, and we haven't even moved yet. Just understanding what is the desired configuration is, or the possible configuration, the configuration that achieves our desired position in the workspace is hard. Yeah.
So, but if there's 6 input parameters and there's 6 output parameters, wouldn't it be 1-to-1, or is it?
The direction for kinematics is a 1-to-1 mapping.
Okay.
But understanding what are the assignment to the degrees of freedom that will achieve the desired position in the workspace is a 1-to-many.
Oh, okay. I guess.
So so this is called inverse kinematics, and we'll see that even that is not enough, and we'll see why we need motion planning. But before that, I'd like you to open up lab 2. This is the most fun one. Well, actually, they're all fun, but I love this one because my students work really, really hard to get a motion planner to work on a Google Colab. So this was a non-trivial task. I think you will enjoy it because you're actually going to have generate simulated robots on your Google browser. So, and an important reminder, now that you're running this notebook, you have to run it with the GPU. Well, you have it on the top of the notebook. You have the instruction of how to change your runtime environment. It's super important because otherwise it won't run. They're very stingy. Oh, and note that there is one cell here that is only relevant if you're running this on Google, so you don't have to run this. Oh. This is not supposed to be a link. So you have this very elaborate explanation on inverse kinematics, which we just covered, so you don't have to read it all. But what is important, I mean, what I want you to focus on is the fact that we have these discrete actions, but now we have to run them in continuous space. So getting an action to actually perform is not trivial. And then we'll have the challenge of taking into account the fact that there are obstacles in the environment. So the task that we should focus on is task number 2, where we are, this is going to, I hope, give the flavor of why inverse kinematics is hard, to answer your question about inverse kinematics. So this is task number 2. You're given you're gonna be the inverse kinematic solver, and maybe you'll solve it very easily, but probably not that easily. My student even wrote, give it 3 to 5 attempts so you don't gain too much frustration. Also note how many words Yuval had to use to actually express what a block exactly he meant, which usually happens in the tasks phase. Did you try? Did you get to a point where you understand why it's hard? Why it's not trivial? I hope. This was meant to create frustration. Hope you're frustrated. But then there is coffee, so it's balanced. Anybody else manage to play around with it? So since we have 3 minutes to the break, and of course, we can continue doing this. I do want to kind of finish this part with a discussion. Let's say you have the capability of actually solving inverse kinematics, or you simply have a solver that tells you, given a configuration, initial configuration, and an end configuration, you can compute a trajectory that will achieve the desired function. Sorry, you can actually compute the configuration that will achieve the desired workspace state. So you understand what is where you want your end effector to be, and you can compute the values of your the freedom to achieve that. Why is that not the full story? Why do we still need methods for motion planning? Why is inverse kinematics not sufficient?
My mind is it doesn't, we have to talk about what's control feasible. Like, it doesn't matter if we know, what the absolute change in position and orientation has to be. We have to know what is actually possible.
Yeah. Okay, so that's one thing, great. We need to know what's possible for the robot, yeah.
Like actually defining a motion that doesn't collide with other obstacles.
That's the other thing. We have to take into account the obstacles. Remember that when we transferred from task planning to motion planning, everything became obstacles, but the end effector itself is one point in the environment, which is not an obstacle, and everything else is an obstacle, and you want to figure out how to move into the space. So now that you know what your target is, you know your initial configuration, because that's given, and we managed to compute using inverse kinematics, and we're going to use methods, off-the-shelf methods for inverse kinematics, as opposed to what you've been trying to do right now. That we have the goal configuration. Now the challenge is to figure out how to actually use the actuators that are available for the robot and consider the obstacles in the environment in order to optimally achieve the goal configuration. So we'll do that after the break. I think this is time for the break, right?